It turns out there's even more we can get out of the definition of radian angle measure. So here's the definition of radian angle measure. An angle theta in radians is s over r, where s is the arc length and r is the radius. But imagine that how all of this comes about is we have a circle that's rotating, say counterclockwise, just to be specific, and its starting position, let's keep track of one point, this blue point on the edge of the circle as the circle rotates. So let's say it starts here on this right-hand side, and after a while it's rotated up to here. So here's its ending position. And this is, let's say this is after some amount of time, and let's call that amount of time t. You could measure t in seconds or minutes depending on exactly what the situation is. So we have a change in position here after some given amount of time t. So let's, just to make the coming algebra a little easier, let's multiply both sides of this equation by r. We get theta times r equals s. And remember, this point on the edge of the circle has moved this distance s in t seconds, say. So to get the time into the game, let's divide both sides by t. So on the right-hand side, we get s over t. On the left-hand side, well, the radius doesn't really change, so let's rearrange our fractions so that the division by t only shows up with the theta. So that's a little fraction trick if you haven't seen this before. It's always okay when you have a multiplication in your numerator, you can always slide one piece of the multiplication off to the side to get a fraction that's the same as what you started with. All right. Well, anytime you divide a distance by a time, that gives you a speed. So this arc length over t, that's really just a velocity or a speed. So we'll call that v, since this is how fast the point on the edge of the circle is moving. And on the left-hand side, we get r times theta over t. Well, what is theta over t? It's some angle that the circle has rotated through in some amount of time. Well, that's exactly like some distance in some amount of time, except instead of measuring how quickly you're covering distance, this theta over t measures how quickly you're covering an angle. And so this also gets called a speed, but instead of a speed in a direction, it's the speed of an angle, and so it gets called, rather creatively, angular speed. So that's what theta over t is. And the traditional letter for angular speed is sort of this curly W looking thing, which is really an omega. So if you're using radians, the speed, this v is called linear speed, since it's speed in a particular direction. So if you're using radians to measure your angle, then linear speed is the radius times the angular speed. And again, I emphasize this is, for this to work, you must be using radians. That's one reason the radians are good. Okay, so let's see how we can use this. So for one example, let's suppose that an ant is riding on the edge of a 4-inch disc that's rotating 3 times per second. How fast is the ant moving over the ground? So I guess we're looking down from above on this disc that is 4 inches in radius. I guess I didn't say radius here, but let's say this is the radius of the disc. And maybe the ant starting here, the disk is rotating 3 rotations per second. And we want to find how fast the ant is moving over the ground. I guess that would be linear speed in this situation. This 3 rotations per second, that's telling you how fast something is turning, so that's an angular speed, so omega. And of course 4 inches, that's the radius. So you can see we have all of the ingredients to use that equation that we came up with a minute ago. Remember, it was linear speed v is radius times angular speed. But wait, this equation has a caveat. We must be using radians to use this equation. So right now we aren't using radians because look, we're measuring this angular speed in rotations per second and not radians per second. So before we can use this equation, we need to convert omega to radians per second. Okay, so 3 rotations per second is what we have. Remember, to do a unit conversion, really you just want to multiply by 1, but you want to write 1 in a way that will do the unit conversion. So we want to get rid of rotation, the rotation unit. That's in the numerator, so to cancel it, it should be in the denominator of our conversion factor. We want to produce a radian unit in the numerator, so put that in the numerator of our conversion factor. And now we just need to write numbers here and here so that both of these angles are the same. So how many radians are in how many rotations? Well, in one rotation, there's 2 pi radians. All right, so now we can work this out to do our conversion. Notice that the rotation units are gone, and the remaining units are radians per second, just like we wanted. And doing the arithmetic, 3 times 2 pi, that's 6 pi. Okay, so omega is 6 pi radians per second. So now we can use our speed equation. So velocity, linear speed, velocity, is the radius, which is 4 inches, times omega, which is 6 pi radians per second. Now we can do this arithmetic. 4 times 6, that's 24 pi. 24 pi. And for the units, we have inches times radians all over seconds. All right. Well, this almost looks good. The only problem I have with this is this unit doesn't make sense. Our linear speed v should be in inches per second. So what's this radians doing here? Well, remember, the unit radians isn't really a unit. It's actually a lack of unit. The word radian is just a note to ourselves that we're measuring an angle. But we aren't measuring an angle anymore, so just stop writing radians. That radian unit was imaginary to begin with, so it disappears. So we get 24 pi inches per second, which is, I guess, about, pi is about 3, 24 is about 25, so that's about 75 inches per second. So that poor ant is moving at 75 inches per second. I hope it can hold on. So you can see this equation is pretty handy, although you do have to be careful to use radians. If you try to use this equation when you're in degrees, you're going to get velocities that are way, way off track.